I'm going to record on this computer because I can't record to the cloud. So that's us recording. Brilliant. Okay, I'm going to make a start because otherwise we'll be waiting. I know that some people need to get away. 3 people's just entered the room. This could be the case. Lovely. One and that. I'm still getting to grips with this Zoom thing.
More familiar faces.
There we go. Brother. Okay. And excellent. Right.
I do like that bridge.
I think we have a full complement. That's brilliant. So now let's see if the technology works. I'm going to share my screen.
Whoa.
There we go. Can you all see the title slide?
Yes.
Yeah, all good.
Fantastic. Okay. If everybody's happy, shall we make a start?
Yes.
Brilliant. Okay. So a very good morning. Welcome along. I hope you find this informative, and I hope that you're all safe and well. So let's make a start on this. So first of all, we've got coffee breaks and comfort breaks scheduled into the presentation about every half an hour. If you do need to scoot off, then feel free. If you've got any questions, if you can prefer to ask them at the end of every session, and that way, because what I might be doing is I will encompass that within the session. So don't call out. Let me get to the end of the session, and then we'll do that. Next, because it's a Zoom thing, if you don't like to mute, apart from me, obviously, and that just saves any sort of feedback, feel free to unmute when you want to ask questions or put a point over. If we have a lost comms procedure, I've got all of your emails. I've got an email set up already on the computer. All I'll do is I'll produce another meeting number, get that off to you straight away, and you'll come back in on another meeting. But hopefully we should be okay. And we've already answered that question, so we'll move forward on that. And a massive, massive welcome to you all. So we'll keep calm and we'll introduce ourselves. I'll just basically stop the screen sharing so that I go around. So my top left is Julie. So if you'd like to introduce yourselves just with what level you instruct at and what discipline you're instructing at as well, and how the stability will affect your lessons. Okay, so we'll start with Julie. You're on mute, Julie.
Yeah, I'm off now. Forgot the mouse. Power instructor and examiner. So yeah, stability tends to be about loading and stuff. I don't tend to go massive detail into it, but I explain to them just which way not to point it in waves and how not to load it certain ways, this type of thing.
Fantastic. Okay, just past me is David, Mr. Wilder. David's on mute. Yeah, bottom left, David. That's it.
Can you hear me now?
Yeah, we can, mate. Yes.
Yeah. Yachtmaster instructor on motor and sail. I teach powerboat level 2 and also teach ocean theory. So that's me.
Fantastic. Thank you, sir. And now Gary Martin, which you're currently on mute at the moment, mates.
Yeah, well, Gary Martin. I'm a CI Power, Advanced Powerboat, PWC, and I don't teach a lot of loading, just more in a practical sense to people in terms of loading and stability. I'm just interested to get a further take on it, and I've seen some stuff you've done before, so I was intrigued to jump on and see where I can add bits to my course teaching.
Okay, fantastic. Doug, good morning.
Morning. I teach across most of the schemes. Stability comes in a few courses, and I'm ready to hear some more and see if there's any gaps in my knowledge where it is.
Lovely. Thanks very much, Doug. David Davini.
I teach powerboat and safety boat. I'm a lifeboat coxswain, so stability for going out on boats and basically giving advice to any other boaters that we come across, whether it be through getting a call out or whether it's just seeing them on a pontoon. But yeah, trying to upskill my skill levels as I progress through the instructor schemes.
Excellent, fantastic, thank you. Peter, Mr. King.
Yeah, on a CI sail, powerboat advance, PwC, and a few shore-based bits instructor. So essentially, I'm here to shamelessly steal any good ideas you have to help me teach it. Thank you very much.
No, you're not stealing them. You're taking them with my consent.
That's the one.
Thanks, Peter. Alex.
Yeah, good morning, everyone. Alex, cruising instructor sail. I'm just here cribbing from the light side, shall I say, from the dark side, just to see how it's done differently in the motor world. But I teach it a little bit, just trying to convince comp crew that the boat's not going to fall over when we're sailing and stuff like that, and just giving them understanding. But I'll be interested to see the differences with the motor side. So yeah, a bit like Peter, a bit like Gary, trying to just pick up bits to take it forwards.
Fantastic, lovely. Thank you very much. Michelle?
Yes, good morning. From Belgium. First of all, I need to get out at 11 o'clock your time, so I'll just sneak out. My apologies for that.
Yeah, okay.
Are you aware of that?
You'll find that the bones of it is in the sort of the first session. So we've got a bit of a pool session with some model boats and things. So you're going to be getting the bones of it before 11 anyway.
Okay. So I'm based in Belgium and teaching sometimes in the UK and a lot in Holland. Yachtmaster Instructor Power and Powerboat Advanced Instructor in inland waterways.
Excellent. Thank you very much,
So,
sir. Sorry, carry on. Sorry, I cut you off there.
Yep.
Lovely. Peter, very good morning to you, Mr. Lawton. You're on mute.
I'm mute.
You're unmuted.
Good morning.
Now. That's it.
PB2s, PwCs, hopefully get my advanced instructors this coming season whenever it starts. And I'm going to do what Peter does, because I've done it from him for years, and that is steal with pride.
No problem at all. No problem at all. Brilliant. Robert, good morning to you.
Morning. Yeah, right. So I'm a powerboat instructor, senior dinghy instructor, and shore-based instructor, working and work with Sea Cadets. So yeah, doing quite a bit of all sorts of different stuff. So like everyone else, I'm going to take with your compliments everything you're prepared to give and reuse.
No problem at all. What I'll say, if I can do, is I might put this presentation on Dropbox and then forward everything to you. But that's no problem at all. Right. Let's see if it works. So I'm going to share screen again. Okay. I just need to go back to my my presentation seems to have gone off. So let's have a look at that. Brilliant. Okay. So we've done that. So a very small disclaimer from me, I'm not a yacht surveyor, okay? In my job as chief instructor for the Combined Cadet Force, I'm a Lloyd's assessor, and one thing I have done is I've gone through the testing process, the assessment process, because both of my vessels got re-engined about 2 years ago. The other thing as well is for my cruising instructor trainer, I was given a sort of a 15-minute lesson to do on stability, and I thought, Christ, how can I condense this down to 15 minutes? And basically my interest in stability just grew and grew from there, basically. Okay, so let's make a start. So here is a video. Unfortunately, it is of a yacht with flappy things. What I would like you to do is I'd like you to notice the motion that the vessel goes over at, okay? Because you can then relate it to some of the theory that you'll get in a minute. So as the vessel heels over, you'll see it'll start to heel over very quickly. It will then start to stall a little bit before it fully goes over. Here's the video.
Professional sailing is no pleasure cruise. Here's the proof in the raw. Amazingly, no one was hurt in that capsize.
Okay, so that's them on a very, very bad day. And you probably noticed the negative righting moment, which is the alternation of the weights, actually snap the mast. So what are our aims this morning? Well, first of all, I'm going to take you through the definition of stability. I'm going to take you through the two forces, the center of gravity and the center of buoyancy, how these two forces interact to give you the righting moment lever, and of course, if it goes too far, the negative part of that. How boats are tested for stability. I'll take you through how my boats were tested. And I'm not going to go too far into the mathematics part of it. I'll stick to very much the practical side. I'll then go through the stability curve, okay, which is the graphical representation of what you will see when you look at the boat's information. Sticking to the motor side of life, we'll take you through some of the features that are on motor vessels that do affect stability. The fly bridge, increasing the weight uppermost, is one of them. Situations that lead to a loss of stability. So we'll be principally talking about down flooding and of course free surface effect. Moving on to the objectives. Okay, we're going to expand on the subject of stability for you guys. I should imagine that, you know, a lot of you know a lot already. We'll be sharing ideas of how to teach stability to students on the proviso that 10 heads are better than one, and how a practical session should run, whether you're out at sea on a boat or whether you're in a classroom. And very importantly, again, 10 heads are better than one, getting some learning points that we should be putting over in a stability lesson for our students. So stability. The dictionary meaning is basically the state of being stable, okay, which is very generalized. The marine version, okay, of definition is basically the ability of a vessel to remain upright in all sea conditions. During my 7 years in the Coast Guard, I experienced that capsizing and swamping, okay, were the most likely incidents to occur in injuries and unfortunately in fatalities. And I think this is one of the main reasons why the RYA training is incorporating this in some of their courses. So let's talk about, first of all, the basics. Let's get to the nuts and bolts, which is the interaction of two forces. The first force I'm going to talk about, obviously, is the center of gravity, which is normally labeled G. This is the downward force of the vessel displacing the water. Okay, it's the force that pulls all things down towards the earth. And it's normally located on the center line. Okay, this is assuming two things. Assuming that the vessel is symmetrical, okay, and assuming that the weight is evenly distributed throughout the vessel. It's the balance point of the vessel. And if you look at me, if you actually see that I'm balancing a pen on my finger, okay, when that pen balances, the actual balance point, okay, which is the center of gravity, is the bit that's immediately above my finger. Look at that, I've practiced that. There we go, success. And it's obviously, it's where the balance point is where all of the weight interacts throughout the vessel. And this doesn't move unless you actually shift the weight yourself. And obviously this force is indeed perpendicular to the surface of the earth. Next, we have our center of buoyancy, which is labeled B. The center of buoyancy is the upward force, okay, of the water trying to return when the vessel, okay, displaces the water. It moves. So basically, when we talk about the center of gravity, it stays the same on the center line, okay? It will move later on when we transfer weight throughout the vessel, but most of the time, the center of gravity stays on the center line. What the center of buoyancy does is, as the vessel heels over, the center of buoyancy, because the actual shape of the displaced water changes, so the center of buoyancy changes as well. And it normally goes towards the lower side of the vessel as the vessel heels. And of course, this force is indeed perpendicular to the water surface. So in a perfect scenario, we have a nice upright vessel, okay, nicely upright on the center line. Let's label the center line. We've got the downward force of gravity and we've got the upward force of buoyancy, okay? And both of them at the moment are working in perfect equilibrium, okay? Don't ask me to say that word tomorrow night when we are, well, Saturday night when we're doing the drinks at the conference over Zoom. I will not be able to say equilibrium at all. Actually, I was quite surprised when I said it then, really. The vessels heel though, okay? So how do they become upright? Well, basically, as we said, center of gravity stays in the same place as the vessel heels, okay? What the center of buoyancy does, okay, is it moves outwards, okay? So now the two forces are out of line. And now what they're doing is they're producing a rotational force in order to bring the boat upright again. This rotational force, okay, is known as the righting moment lever. The Americans and the Canadians tend to call it the righting arm, okay, but for today we'll leave it at the righting moment lever. And it's normally labeled GZ, okay? The G is obviously for the center of gravity. The Z is the center point of the center of buoyancy and the upward force. And it's normally, if you have a look at the position of it, it's normally at a right angle to the direction of the downward force, okay, interlinking with the center of buoyancy. Some other diagrams tend to produce it differently, but I've gone through a few of the diagrams and most of the time it's this way that they represent it. So that's called the righting moment lever, and that is the rotational force of the vessel wanting to return back to the upright position again. And of course, this always goes around the balance point or the pivot point of the center of gravity. So if you think that that is the pivot, the lever is levering the whole thing upwards, and that's what's causing the vessel to come upright again. At this point, I think it's fairly important to stress a couple of meanings to you. First of all, heeling, okay? What heeling is, it's the tipping of a vessel due to an external force. So if you're in a sailing boat, it's the wind on the sails. If you're in a motor vessel, it could be the wind on the superstructure, or it could be the seaway. But that force is normally temporary. And when that force ceases, the vessel automatically becomes upright again. Listing is different. Listing is actually the vessel leaning over, okay, due to the weight location, okay? So what happens is when load masters of ships and they leave dock, their principal job of the chief officer is to make sure that the weight is evenly distributed and that the balance and all the things are correct. And as we saw a couple of instances in the Solent, okay, the Hoga was one where they actually got the ballast wrong, and actually the weight above was actually more than what the ballast was. Hence, we had the heeling over of the vessel and hence the grounding in order to save a catastrophe. So with listing, the only way that you can bring the vessel back to its upright location again is either you counteract that weight with another weight, or you get rid of the weight that is heeling over the vessel. So how is all this measured? Well, what some surveyors do, there's a couple of methods here. What some surveyors do, okay, is on the center line, what they do is they then extend the force of buoyancy up to the center line. And where these two lines meet is known as the metacenter. Okay. The metacenter is an abstract reference point, okay, hence the term meta. And these are where these two lines intersect, okay. Obviously, the higher up it is, the better seakeeping capabilities that vessel has. And surveyors use this to determine the vessel's ability to remain upright. There is another measurement that's introduced into this though, okay. So from the metacenter, going down to the center of gravity of the vessel, okay, the length of this line is known as the metrocentric height, okay? And basically the longer the length of this, again, the better seakeeping of the vessel. because the longer the metrocentric height, okay, the lower down the point of gravity is, okay, and the point of gravity on a vessel stability is really quite critical. And they have better sea keeping, better rolling effect. And as you can see with this, you've got a nice long righting moment lever, GZ. And that causes the vessel to come upright again. So to know how these 2 points interact with each other, it's important to know what we call the stages of capsize, okay? Now, even this boat is over at 90 degrees. You think to yourself, oh my word, you know, all is lost. However, you'll find that even at 90 degrees, most vessels will still have a bit of righting moment, okay? And this is reflected, okay, in the fact that, you know, you have a high weight distribution, bearing in mind that weight could move at this stage. But the righting moment applies here, but only just. The second stage of capsize is when the vessel goes over at about 110 to 120 degrees, depending on the vessel. It's important to note here that each vessel is very different. Now what has happened is that B has moved immediately under G. So what you have is AVS, which is angle of vanishing stability, okay? The righting moment has now gone neutral, okay? Further into the healing process, okay, you've now over at 120 degrees plus, okay, the righting moment is now negative because that rotational force is not righting the vessel. That rotational force is doing the opposite effect of inverting the vessel. So basically the forces are now acting an opposite effect, and instead of righting the boat, they are working together to invert the vessel. And of course, our friend there is swimming away. And of course, because there's a shark behind him. Let's try to make the subject less dry, to be honest. So now what we have is the final stage of capsize. The boat is now fully inverted, okay? And as we can see, G is over B. The boat is in a very, very stable state, okay, which is the good news. The bad news is the boat is inverted and is unlikely to return. So what I've done is I've put all this together in a video. So if you'd actually notice the scale on the top line above the vessel, that's going to be the actual righting moment curve forming in front of you. And also note the movement of Z, which is actually the center of buoyancy. So let's run the video. You can see how Z moves out. Right, the righting moment curve takes shape. It now lowers. Force of buoyancy goes underneath the force of gravity, which is now AVS. And now the negative GZ is inverting the vessel. All happy? You had a bit of a perplexed look on your face, Alex. Is everything, did you see it all right? Yeah, great. So how is all this tested? Okay, well, they don't do that, obviously. What they do is this, but I'm not going to explain all that because I'm not a mathematician. I'm a little bit dead in the water when it comes to maths. So what happened with my vessel is we re-engined from heavier 122 alpha Volvo engines to much lighter Volvo D9s. And what happened is we actually saved about 95 kilograms of weight per engine. And what that did was it drove the weight saving past a certain percentage, okay? So what happened was the Lloyd surveyors had a look at it and said, no, we've got to reevaluate and give you another stability test. So what happened? Well, this test happened at Port Solent. The craft, both of my craft was afloat in the still water with all the moorings nice and slack. We made sure that the craft was fully loaded with a full complement of kit, okay? Full water tanks and full fresh tanks so that the vessel was literally fully laden, okay? And my vessels fully laden are around about 27 tons. So compared to other vessels, they are very, very heavy indeed. And you'll see this in the figures a little bit later on. We had personnel on board. Now, if you can't find personnel, then you're going to have weight. And what they normally do is they normally use iron ingots for this. what I did was I had the weight standing by, but instead of iron ingots transporting it down to the jetty, we had water jerry cans down to the jetty because it was easy weight. It was a case of, you know, we filled them up with a hose before we used it, and then we emptied it and it was nice and light, and we trolleyed all the jerry cans back up afterwards. So that's something for you to consider. So then what happened is we didn't really need to use the jerry cans because we had some strapping lads from the boatyard, all 10 of them. All of them got individually weighed, and all of them were placed on the vessel. And it was nice for them because they got a quick 15-minute tea break as well. So the vessel was in level trim. And what they do, as per the diagram, is they take the freeboard measurement from the gunwale down to the waterline. Also, there's a clinometer, there's an electronic clinometer on the center of the vessel as well, to make sure that they're not just taking one set of figures. One set of figures is correlating with the other set of figures. So the freeboard was measured. Then what happened was the personnel rapidly moved over to the port side. It wasn't a case of them stepping over nicely and carefully. It was a sort, it was meant to impersonate a rush of people over to the port side, and there was a special float marker on the side that actually went up and stopped when the vessel stopped heeling over. I'm doing a lot of yacht and karate now. Then the same deal, okay, was moved over to the starboard side, okay. The helmsman, which was me, I didn't move because obviously it was impersonating me still being at the helm on the fact that I never move from the helm. And then what they did was they got their calculators out, okay, checked that one correlation matched the other correlation, and then they produced this certificate. A couple of things to notice on here, okay. If you go to the freeboard, okay, you'll actually find that there's the measurements. What was required was above 627 millimeters. Actually, what I produced was 1,250 millimeters. So a hell of a lot more stable. So I only heeled over at 3.5 degrees, where in point of fact, what the requirement was, you know, heeling over less than 7 degrees. So it was absolutely brilliant. And this reflected in the weight. So now I am certified for 10 people, okay? Instead of 75 kilograms per person, I can now take on board more rotund people, okay? Because now my weight's gone up to 82.5 kilograms. Whoever's at 82.5 kilograms, I honestly don't know, but there you go. So this is all represented in a stability curve, okay? And it's a graphical representation of the stability of that vessel. And what comes out of this is the recommendations both for loading and for the sea conditions that vessel can actually go out and operate in and safely and be safe at the same time. So let's build a stability curve. So first of all, here we have our y-axis. And here we have our x-axis. And of course, we've got our origin, which is 0. So above the origin, we have our positive part of the curve. And of course, in opposite below, we've got our negative part of the curve. On the y-axis, okay, is the length of the righting moment lever. It's normally expressed in meters and in sub-units of meters, okay, depending on what vessels you've got. So there's our scale for that. And I'm not going to label the scale because it could be anything, so long as it's in meters. But that is the length of the righting moment lever, okay, from the downward angle of the center of gravity, okay, over to the center of buoyancy, as worked out on the calculations. Along the x-axis is we have our angle of heeling. So there's our scale. Okay, 20 degrees, 40 degrees, 60 degrees, 80, 100, 120, 140. You're getting the gist. Now we have our actual curve itself, okay? And the various points are put onto the graph in order to create the curve, okay? And this is the positive side of the curve. So if we have an angle of 60 degrees heel, this is the amount of positive righting moment that this can actually produce. Therefore, this part is called the range of positive stability. Now, as with anything, okay, as the vessel heels over, you'll notice that the righting moment gets stronger and stronger, but it gets stronger only to a certain point. And that point on this graph is round about the 60-degree mark, okay? From there, it gets less and less. So you probably saw, going back to our video of the trimaran, you probably saw how the initial heeling over was very, very slow. It then speeded up. It seemed to hold itself for a little while, and then it went over. And this is basically the graphical representation of that. Then, of course, we have our negative part, and when it goes through the x-axis, okay, to go to negative, this point here is, of course, our angle of vanishing stability, okay, which is the balance point. So from the green part, you've got the center of gravity and the center of buoyancy creating that righting moment to bring the vessel upright. You then go through the angle of vanishing stability. Then it goes into what we call negative GZ, okay, negative righting moment. And those two forces are reversed, causing the vessel to invert. So AVS is normally when the center of gravity and the center of buoyancy points are in line with each other. At this point, the righting moment lever completely disappears. Further on, okay, the points are reversed, causing inversion. And these results are used to determine the safety range of the vessel. So basically, you're looking at MGN 280 for your vessels. With my vessels, I've got the Royal Navy, I've got the cadet vessels under training of float regulations and safety, and I've got Lloyd's, and I've got MGN 280. So I've got to conform to a hell of a lot more. And of course, just to remind you that the unit of measurements is the righting moment, okay, and that's in meters on the side scale. So with your mute turned off, let's have a look at a couple of vessels, okay? So we've got the light plastic Fantastic on the left, okay? Actually, I'm a little bit mean with that, actually, because the Bavaria is actually a reasonably weighted boat, okay? But it's light plastic Fantastic. It's obviously got a higher, fly bridge, okay? It's a little bit lighter. And then in the shed, just to show you the keel, you've got one of my vessels, which is the semi-displacement hull. So the question to you chaps is, which has the highest and lowest angle of vanishing stability? And what are the things that you're considering in order to get to that answer? So does anybody want to come in on this? Just shout out, Peter.
I mean, obviously, hull shape's going to come into it. You're a more curved shape, so you're going to have a more gentle roll.
Hull shape, yeah.
The plastic Fantastic's flat, so it's got a more sudden curve. The engine intakes on the plastic Fantastic is guessing as soon as the water gets to them, it's going to lose its angle of stability. Whereas looking at your boat, I don't see any shiny metal bits on the side for engine intakes. So I'm not sure how they'll affect.
They're above. They're just above the tow rail.
Yeah,
so
so
you've got the angle of that photograph. You can't really see it. Anybody else?
The ballast of the displacement boat is going to give it a higher AVS. It's going to have a better righting moment till later.
What does that do to the center of gravity, Doug?
Takes the center of gravity down, increasing the.
Yeah. So when you go back to that diagram with the metrocentric height, it heightens the metrocentric height by driving the center of gravity lower. So therefore, you're always going to get a better righting moment lever. Brilliant. Anything else, guys?
Well, just looking at your boat versus plastic Fantastic, there's a little bit more weight. There's obviously more weight lower down. There's more of the boat in the water and less of it on top, basically, isn't it?
Fantastic. I think we've got the gist on that. That's brilliant. So yes, unfortunately, there's some more flappy things. So just to let you know, for the race yacht on this graph, you're looking at about 90 degrees. Okay, it's lighter. The other thing as well, actually, that to consider is probably waterline length as well. You know, the actual beam of the hull might have something. It'll be a very, very small part of it, but it will come into, it is a factor, as you like. So basically the blue water cruiser, you've got 120 degrees before it goes to AVS. Okay, for the light displacement hull, 90 degrees. So there is a little bit of difference there. One of the things that you get this information from is that all yacht manufacturers have to put this on their yacht's information sheet. And one of the things that I do say is take note of this. The data is supplied by the designer and builder. So I think the sentence salt and pinch, okay, that includes those words should come into play. Treat it with a pinch of salt, because there is no independent body at the moment that says you must produce this and this has got to be accurate. So treat that with a bit of a pinch of salt. But this will also be the loading recommendations, okay, and they also provide a stability curve for you as well. And you can actually compare different yachts with different stability curves. So they have the builder's plates, okay, which is the CE plate, and that's the minimum standard for that vessel, okay. And again, check with countries. Obviously, we're under the umbrella of the European Union. Now that we're not, things could change. So check with the manufacturers, you know, if it's a different country. So the minimum standard for that vessel is displayed. So A is ocean, B is offshore, C is inshore. And this obviously affects the code of practice for commercial vessels as well, because you know, mine is Cat 2, okay, and that comes within those guidelines as well. So what we're going to move to later is, why do vessels lose stability? So we'll look at differences in motor vessels. We'll look at a higher center of gravity, the higher weight. Okay, we're going to have a look at some case studies, and then we'll explore down flooding and we'll explore free surface effect. So motorboats, okay, how do they differ to yachts in stability? What helps or hinders them? So first of all, just do a show of hands. Okay, we have a smaller keel, so there's less weight below the hull. Does that help or hinder the stability of a motor vessel? So thumbs down for hinder, thumbs up for help. Yeah, we've got a few thumbs down there. Fantastic. How about a wider beam? Helps or hinders? Yeah, helps. Lovely. Higher structure. So you've got a wheelhouse, you've got a flybridge. Yeah, okay. So at the moment, it's not looking good for us motorboaters, is it? More people aloft up on the flybridge. Yeah. Less immersed volume, so more of a broader hull shape. What we think? Yeah, more or less. And bigger internal areas, so there's more chances of free surface effect. So we're not really on a roll here, are we? And of course, the weight of engines, which we'll explore later in the practical session. So weight of engines. Yeah, that's so always end in a plus. Okay, so that was a sort of an elongated Preisberger. So anybody got any questions? Unmute yourselves. Anybody got any questions so far?
Can I ask a quick question, Gary? You were talking about the ratings, and I read that they did a score out of 100, which was called a Sticks score. Is that still current? Will you cover that later?
That I'm not quite sure about that. I've not come across that myself, but I'll have a look. I'll have a look at it. But it'll be interesting. Does anybody else have the answer to that one? No. Was what regulating authority did it come under, David?
Let me send you the information that I got, which I think I derived originally from the MCA.
Okay.
I've heard of Sticks before, but I can't remember exactly. I thought it was a racing measurement rather than a coding measurement, but I'm not 100% on that. So it's a vague memory coming through there.
Are you? Is this related to sort of like IRC rating?
Yeah. So Peter's right. Sticks was devised by Rourke for IRC. I've not heard of it used for motor vessels, but I suppose it could be. But it concerns itself with the same sort of stuff.
Yeah.
but it's used by our coding surveyors.
Okay.
Although they may use it as a basis before coming up with their own figures.
Brilliant.
I came up with it because I was looking at how I could teach stability better, and it came up on stuff, and I thought, well, I didn't quite understand it, and therefore I'm not going to teach it anyway. I thought I'd ask as we were doing this session.
Yeah, okay. Well, no, what you've done is you brought that subject to the front. So what I'll do is I will actually have a bit of a look at that, see how it relates. And if it
I'll
does
send
relate,
it to you in
I'll
one
send
of the
that
breaks.
information out to everybody because I've got everybody's email address. So please send me that. That'd be great. It just goes to prove these things are always a two-way street. Okay, gang. So let's have a quick 5-minute comfort break. So nab a cup of coffee, go to the loo, whatever you want. I'll see you guys back at 10 to 5 minutes. That gives you about 6 minutes. Okay. Happy days. There we go. Let's go back to the shared screen again. And let's see if I can go back to that one. There we go. Lovely. So everybody happy? Everybody can see? Yeah, lovely.
Yes.
I think we're missing Mr. Loughton. Peter's done a runner.
No, what it is he's on a low bandwidth, so he switched off his audio and he switched off his picture as well.
That's his excuse. He's having a kip.
Right, okay. So let's have a look now, move on, and let's have a look at the weight and its effect on the on stability. So obviously consider the safety of the vessel if you're moving any weight. Okay, it will minimize the stability. And what we're going to do in this session is we're going to have a look at vertical and horizontal movement of weight, and we'll start with vertical. So here we are on the center line, everything is happy. What we'll do for a motor vessel, let's add some weight and let's add some height. So there is our wheelhouse. Let's add a flybridge as well. And more so, let's add Charlie's Angels to the flybridge. I'm just seeing if anybody's smiling because to see exactly who's giving away their age, knowing who Charlie's Angels are. So how does vertical weight, what does this do to the center of gravity? Well, basically it raises the center of gravity from there to there. Okay, I mean, these aren't exact on these diagrams, so again, don't take that as read. But more importantly, again, shown from the calculations, okay, what this does is it lessens the metrocentric height, and therefore it does affect stability, and we'll show you how it affects stability in a minute. So basically, if we move weight vertically, what's going to happen is the center of gravity is going to move vertically as well, okay? If we have a lower center of gravity, it makes everything a bit more stable. If we have a raised center of gravity, it makes things less stable. And also, if we add weight to the vessel, remember that weight reduces freeboard, okay? And again, that will be quite prevalent a little bit later on when we talk about down flooding. And the center of buoyancy is moved upwards as the freeboard gets less. So now let's produce a heeling situation to show you the righting moment curve, okay? So the boat heels over at 20 degrees. There is our force of buoyancy. There is our force of gravity. They're not acting in equilibrium anymore. The center of buoyancy is moved outwards. There it produces a shorter righting moment, okay? Because what actually happens is with a higher center of gravity, okay, it actually makes, okay, that the actual length of the righting moment is lost in the gaining of the height of the center of gravity. Okay, so that makes for a much shorter righting moment lever. So the boat is much less sea friendly. The center of gravity is raised, and this causes a shorter righting moment as a result of the higher center of gravity. It has a less chance of righting, becoming upright, okay? And again, the recommendations for loading and the places for loading should be on the CE plate. And the case studies that I will show you later will demonstrate this. So let's have a look at horizontal weight. So for that, we need to build a crane. So let's build a crane. So there's the jib. There's to hold the jib up. There's that. And I tell you what, we need a bit of weight as well. So let's put a ton weight on it. Okay. So how do you think having weight at the side of the vessel, what does that do to the center of gravity? Anybody? Goes up. Okay, so we know it goes vertically, but what else?
Moves horizontally.
It moves horizontally as well. Okay, so as the vessel heels over, okay, the center of gravity, okay, moves in a diagonal situation. So it's actually moving vertically and horizontally at the same time. What does that do? Well, the danger is that if G goes over B, then we are into AVS straight away. So we're in a much more of a situation here than we would do with vertical weight. And as you can see, the righting moment lever is much, much shorter due to a lesser metrocentric height. So moving weight horizontally moves the point of gravity, moves horizontally as well as vertically. It raises the center of gravity as weight is lifted. And the conclusion makes the righting lever very, very much shorter indeed. Now we've gone over a little bit further. So now we can pretty much say that we're over at 30 degrees with the weight. What has actually happened is G has moved over B. This causes the point of gravity is moving horizontally and vertically once more. Righting lever completely disappears, so we're now into AVS, angle of vanishing stability. And this produces a high risk of negative GZ, okay, negative righting moment, because we've got a weight helping us as well. So just with this diagram, again, apologies for the fact that it's a keeled yacht, but this actually shows that as the center of gravity moves up the center line, okay, the actual righting moment, the length of the righting moment lever, GZ, gets less. Okay, so from CG1 to CG3, you can actually see it getting less and less the more the center of gravity moves up the center line of the vessel. Note that the displacement mostly stays the same, and notice the changing length of the GZ. So lower GZ, okay, is also lower center of gravity, gives you a longer righting moment, okay, more chance of keeping upright. Now we come to down flooding, okay, so down flooding, okay, is not just water coming into your vessel. What down flooding should be understood as is it's the additional adding of weight in a dramatic fashion, okay. So if your vessel down floods, okay, you're going to be adding dramatic weight. And think back to the two previous slides about horizontal weight and vertical weight and what that is going to do to the center of gravity in relation to the center of buoyancy. So here's a question for you. What was the earliest recorded down flooding incident? Anybody got any answers to that? Just call out.
Mary Rose.
Oh, look at that. There you go. Okay. So sinking of the Mary Rose in 1545. Yeah. Gust of wind took the boat over. It buried the gun ports. Water zoomed into the gun ports, added that dramatic weight shift to the vessel, and the rest, as they say, is history. This isn't another down flooding incident. This was the creating of an indoor swimming pool at Christmas on the Prince of Wales. The problem being is that the indoor swimming pool was either in the electrical space or the engine space, which didn't really do much good. However, with down flooding, engines need a lot of air, okay? If you have a look at my engines, my Volvo D9s, okay, and I've got this written down here, they need, okay, 2,935 cubic feet of air per minute, okay, if the throttles are fully down. Now, how did I come out at that? Well, I decided to do a bit of study into this. Basically, to work out how much air your engine needs, okay, you basically times the horsepower by 2.75 and take away 90. And the answer will be how much air your horsepower engine needs. So bit of a different plane, but again, every day is a school day. So engines needs lots of air. So your air intakes are absolutely vital. And up to now, they haven't produced any filter that doesn't let in water and lets in air, okay? So at the end of the day, your air intakes are literally that. They're gaps to which air goes in, and there's nothing to stop the water from going in either.
Gary, can I just comment on something you said there about the
Please do.
Volume of air? Because I try and explain that fact that they need lots of air. And I go back to swept volume. So we talk about the engines we've got, whether we've got D9s or whatever in a boat. And then say, imagine that we've got a 1 litre single cylinder engine. How much do you think that's going to use? Most people haven't got a clue. And you get to the fact that at 2,000 RPM, a 1 litre swept volume will use 1,000 litres of air, which is the same size as a builder's bag.
Yeah.
And then I say, well, we've got, 12 litre of engine here. So that imagine getting 12 builder's bags full up into this cabin, and it kind of brings it home. Just mention that.
That's a good way of putting it. Yeah. What this one was as well is this is for engines with turbos, which is more prevalent to the vessels that we operate on the motor side. Okay, you happy with that, David?
Yeah, totally. Thanks.
Okay, no problems. Right. So basically, it's not only air intakes and extraction systems that we've got to worry about. We've also got to worry about hatches and portholes as well, depending on what your vessel is. Down flooding is obviously more prevalent on motor vessels, okay, for the fact that you do have your openings. It dramatically adds weight in a very, very short period of time. And it normally occurs in large spaces such as the engine room. And we all know that with water, with a large space and a heeling motion, will also give you a bit of free surface effect as well. So continuous heeling motion, and this grows through time, okay? And we'll demonstrate that when we get onto the free surface effect. So on this diagram here, you've got 2 locations of air intakes, okay? One is just at the height of a very large hull, and it's just under the gunwale. And you've got the other one, which is on the side coamings of the wheelhouse. But you'll actually find that both of these vessels, the down flooding angle, okay, will be about 40 degrees. Why is that important? Well, down flooding, okay, will occur before AVS, and down flooding will also add to AVS in a dramatic fashion. Let me take this a little bit further. So here we have the stability curve of a fishing vessel, okay? If you actually note, the down flooding angle is 48 degrees. This is well before the AVS angle at 74 degrees. So what's going to happen here? Well, the vessel's going to heel over at 40 degrees. That's going to introduce down flooding, okay? Down flooding will then dramatically add the weight to the vessel, okay? And if Mrs. Downflood comes along, you'll be fairly sure, bet your bottom dollar, that AVS is not far away. So when we talk about down flooding, AVS is pretty much out of the overall equation. We don't need to worry about it, because what we do need to worry about is down flooding, because it will lead to AVS quite quickly indeed. So main points of down flooding is it happens air intakes and extraction points, okay, hatches and openings. The angle of down flooding will be well ahead of AVS. When down flooding occurs, AVS will come very, very quickly indeed. Check water freeing arrangements to that end. One thing that I have on my boat is I have level detectors. So as soon as the level becomes 1 inch above the plate, my alarms will go off, and I need that for the size of vessel. And the other thing as well to consider is the immediate removal of water, not by getting into that space, but removal of water remotely from that space. Okay. So one thing that MGN dictates is that you've got to have 2 to 3 independent ways of moving that water. So what we've got in my vessels is we've got electric bilge pumps with a backup electric bilge pumps. Okay, that's a scarifier pump. We've also got a system where you've got the pipe going from the seacock to the engine pump has got a T-piece that goes down to a valve, which then goes from a strainer box in the bottom of the bilge. So I can actually get into there and open that, shut the seacock, open that, and then the engine pump is actually taking out the water. And I have also got manual bilge pumps that I can pump from the wheelhouse as well. Okay, so that satisfies MGN 280. Free surface effect. Okay, so what is free surface effect? Well, it's the removal of water from one side of the vessel to the other. Okay, dramatically moving weight, and it's perfectly demonstrated by one of these. Okay, so if I'm using this as a tank, it's upright. Go from side to side, there's not much of a movement of water there, okay? However, okay, if I take the bottle and balance it on my finger, now the longevity of the space, okay, and we're moving the water, you can actually feel the power and the weight movement very dramatically. And I think that that is actually, you know, it's only a very cheap water bottle. It's a perfect way of demonstrating free surface effect to your students, okay? Rapid transfer of weight from one to the other, and that is your free surface effect. So free surface effect, okay, there's the center line of our vessel. There's our center of gravity and center of buoyancy. What they have is a buildup of liquid, okay, that can dramatically move in a large area. And it moves around the vessel very, very quickly in that space. It seriously affects stability because of the dramatic movement of weight dramatically moves the center of gravity. And of course, if the center of gravity goes over the center of buoyancy, then we are into AVS very, very quickly indeed. And it grows with time as the vessel tries to right and then heel over again, right and heel over again. That momentum will grow and grow. Normally stored liquids or ingress of water. However, having said that, most of the instances where I had vessel capsizes was actually fishing boats, and the weight that moved was actually the fish stock. So the fish stock went down into the hold, they forgot to put in the retaining boards, and then as the vessel heeled over, all the fish moved over to one side. There is your free surface effect. Okay, so it's not just water, it can be other things as well. It dramatically changes the location of the center of gravity, and the interaction between center of gravity and the center of buoyancy is the same as shifting weight, but obviously more of a dramatic fashion. That way and that way. So to this end, okay, again with a meaning, if you're talking about a tank and that tank is full of liquid, it can't move. So that is treated as a solid mass, okay, because it can't move its weight dramatically the same as free surface effect can. Most vessels have multiple tanks. So my vessels, I've got port and starboard engines, okay, I've actually got 4 tanks. So I've got 2 tanks either side for that fact, so that if the tanks get half full, we're not promoting free surface effect in those tanks. The other thing as well is it's always a good idea to have sealed in bulkheads and small internal spaces. Have high stringers, so if you go into any engine space, you will know that the 2 central stringers that actually hold the engine mounts are very, very high. They're not just high for the engine mounts, they're actually high as a barrier to free surface effect. And obviously with a small craft, pump your bilges regularly and check your engine space for signs of ingress. So small tanks, so there's our liquid. So what they normally do is they have small tanks, okay, and that stops. They're just getting liquid out of one tank either you know, in a given space of time. That will kill the free surface effect. And of course, you've got your high stringers. So any water leaks into a certain place, it's behind that stringer. And again, it can't move, it can't produce free surface. Free surface effect in a vessel. Okay, so as we know, it's moving the center of gravity the same as the shifting weight. I know I'm repeating myself. It's much more dramatic, and it actually assists in the rolling of the vessel. Okay, so it's actually providing a pendulum, a momentum to heel the vessel, and one feeds and adds to another. That then moves the center of gravity, and therefore the man is swimming again, and he's avoiding the sharks again. So I've done a couple of case studies into this, and what came up in my internet search was this vessel here. This is a Silverton 34. It's a very popular American vessel, and the reason why it's popular is it's very, very small size. It provides you flybridge and everything else, but as you can imagine, it does have some stability problems. So let me elaborate on that. This is the first case report, the Candy one. The Candy one went out and they went to watch the 4th of July fireworks in Long Island Sound. The CE plate for loading suggested for crew. Have a guess how many crew. Show your fingers and have a guess how many crew. I think Pete's on the right side of things. 27 crew members on board. Absolutely crazy, okay? Most of them were detailed to be on the flybridge at the time. So there is where your disaster happens. The boat capsized and unfortunately did not recover. Okay, and there was 3 children that were trapped in the cabin, unfortunately died. So basically, if you have a look at the stability curve of this report, okay, one thing that's very much highlighted, okay, is each person reduced the righting capability of the vessel, and the decreased downflood angle was 42 degrees to 39 degrees, which was a change of 3 degrees. Do you get that? Oh, sometimes I waste my time. Okay, so that was that report. The next report was the Khaleesi. Again, roughly along the same sort of lines. It was in San Francisco Bay watching the Blue Angels. And basically it capsized and sank. Fortunately, this time round, there was no fatalities, but 2 children were rushed to a local hospital in critical condition. The problem there was exactly the same, okay? It wasn't free surface effect, it wasn't down flooding, it was a case of just too much weight aloft. This was the test that they did in the accident investigation. Just have a look at that picture and just note exactly where the waterline is on the bow. Okay, basically your freeboard is reduced drastically. Okay, and you've got a lot of weight that's above deck level. So basically, you're raising up the center of gravity quite dramatically on that one. So basically, I counted about 20 people on board that vessel.
Sorry, Gary, was that a test they did, or was that a picture of the actual boat before it went?
That was the test that the American MAIB did.
You'd have thought they put some life jackets on them, wouldn't you?
You would have thought so, yeah. So findings. So basically, always consider your downflooding openings. So watertight integrity in case you need to shut them, and the construction of all your openings. The downflooding angle, okay, so determine what your downflooding angle is, because that's obviously more important than your AVS angle. Always conduct an offset loading test if you feel the need requires it. Always have in place the detection and the immediate removal of water. So alarms in place, drains to remove free surface effect, and water pumps. And again, anybody got any questions?
Yeah, I have. When you were talking about the air intakes, it occurred to me that obviously a lot of vessels' air intakes are quite low down, and I mean in pleasure cruising, and they're not higher up. And I was thinking, oh, it'd be better to put them up. But when you showed the diagram, you said that there was no difference between the ones that were higher up or lower down. And
yeah, what I said, and I should have really clarified it, Gary, is that on those two diagrams, because you've got a higher hull, the actual openings were the same sort of height. If you noticed on the diagram, one of the things that you should look at. Particularly, I'm trying to think where they are on Steve's boat. I think they're actually lower than the gunwale. I think they're
they most definitely are.
Yeah. So it'll be interesting. Have you ever had a look at Steve's stability book on board? Because it will tell you what the angle of the hull openings are for the air intakes.
No, but I've got the survey report in my office here. Actually, as it happens, I might have a look later.
That will definitely be on board. That will definitely be on it.
Yeah, they are. They're low down. They're about sort of halfway between the gunnel and waterline.
Yeah. Okay. Right. Anybody else got any questions at all? Okay. I was going to say have another comfort break, but that's gone quite quickly. That's another sort of half an hour, I think. Do you want to go on a comfort break? Yes or no? You want to carry on? Because we're all having fun.
Quick 3 minutes.
Okay, David, we'll do a quick 3 minutes.
I can always have more tea.
More tea is always good. More tea, Vicar.
I suppose on the note of adding weight higher up aloft, I know on sailboats, if they do go over, by adding buoyancy higher up aloft, you can actually make them less stable in their inverted position, can't you?
Yes, but isn't that sort of shutting the stable door after the horse is bolted to a certain degree?
Yes and no.
That's designed to kill inversion. It's not designed to kill the healing process.
Well, it depends on what type of sailing you're doing. You know, if you're offshore sailing, I mean,
sensible sailing and unsensible sailing.
Yeah, like my boat, for instance, it's the racing version of it was criticised in the 79 Fastnet because it was just as stable upside down as it was the right way up. Whereas the cruising version, they built the cabin on top of, so if it was upside down, it would actually pop back up the right way round.
Okay.
Like, not that really affects the type of sailing I'm likely to do, but
yes.
Yeah, in extreme conditions, it might be nice. Yeah, for the lifeboats and Thunderchild, even upside down, they'll always pop back up because they've got the buoyancy up top. Not so much a cruising boat.
I tell you what really is interesting, and I might suggest this at the end when everybody's back. But have you ever seen the crash test yacht for Yachting Monthly?
Yeah.
When I do ISAF courses and I play that video because of the capsizing, and they put all the cameras in there, and one, it gets you the perfect motion of it going over, and then it's losing AVS, then you're going into negative GZ. But the other thing as well is, because there's cameras all over the place, it just gives you a really good insight. The fact that they didn't put any stops to the gimbals of the Kuka came out, and of course, when you're talking about a Kuka of that size coming over towards your bunk, it's not going to make for a very happy day.
Yeah.
So that was really interesting, and I thought that the dismast it, turn it over, capsize it, and then blow it up with a gas explosion. I thought that was the best thing to do to a French yacht ever.
They're a great series of videos.
Bearing in mind that I'm hoping that you don't own a French yacht.
No, you're all right. Yeah, they're a great series of videos, really. I mean, I do recommend.
Well, the dismasting part, where they first of all used normal bolt choppers, and they found that because the high tensile stainless just slid. They used the hacksaw, couldn't even make an indentation, and to try and keep the hacksaw blade in one area while the boat's moving. The best method, if you don't have any specialized equipment, is literally to undo the bottle screw and take out the toggle. And then after that, they use one of these fancy, 1,300 pound diamond hydraulic cutters, which just cut through it like butter. Pump it 15 times, press the button, and wham, and it's straight through.
And the sinking one, the fact that they were trying to put a hole in the side with a sledgehammer and still having trouble with it.
Well, the other thing as well is what they did was they replaced one of the bottle screws on the mast with gun line, and they thought that the gun line would snap and the mast would go over, but the gun line, even with a full set of sails, the gun line actually kept in situ and held the mast.
Yeah, I'm going to have to go back and rewatch them. It's been a couple of years since I've seen them. So a good set of videos.
Yeah, absolutely. Okay, is everybody back? Just have a look. Julie's not. Peter's not. Doug's just got back.
Don't think Julie's coming back.
Julie said she was leaving at 11, but I've still got. She's not left the meeting.
She said she sent
try
a
and
message.
get back to it.
Okay, that's cool. Right, in that case, I think I'll make a start. I think everybody's there. Yep, I think everybody's there. Okay. So the next case study that I did was the Barden. This was a Northern Marine. It was an 80-foot boat originally, and then it went back to the yard to get extended to 85 feet. What was interesting about this one was it wasn't on the water when it capsized. It was actually being launched down a slipway. And what came out of that is that when you do launch a vessel, down a slipway, because the front is being held by the forward part of the cradle and the back goes buoyant, you actually create a negative GZ initially. And basically the actual, the trim angle caused the vessel stern to come up, while the bow was still supported, and it caused a very, very momentary negative righting arm initially. So the boat went over reasonably quickly, and there's the end result. So what the cause of this was you read the whole report, and it was a catalogue of errors. It was temporary staff. They had 3 different surveyors, so the same surveyor was not working on the craft the whole time. And it basically produced a very, very low margin of stability, because due to the efforts of recording the error, the vessel, the weight was very, very drastically underestimated. And the other thing as well was that in turn affected the vessel's center of gravity. So they thought they installed the ballast, but they hadn't installed all the ballast that was initially recommended by the surveyor that departed at the very start of the project. So the important lesson was that there was 4 engineers in the engine space at the time, and what they had to do was crawl through a service hatch and smash a window in order to get out on the high side. So always when you're in the engine spaces of vessels, and I know that there's a lot of vessels where you just pull up the floor and you go into the engine space from the wheelhouse. But on my vessels, you've got to go down a ladder and you've got a trapdoor. Okay, so one of the things that I'm going to do is to produce you know, those day glow signs and lights, so that if the lights do give out and the vessel goes over, you've got a chance to actually get out the hatch, because I've got sealed in bulkheads. That hatch is the only way that I am going to get out of that vessel. So that is a little bit of food for thought. Because of the destroying of the woodwork and the engines and the electrics, the boat ended up as a complete total loss to the value of $10 million US. So it's not just small vessels that go overloading, it's actually getting the calculations wrong on very big vessels as well. So what we're going to do is we're going to play stability. I've got my tank down here. We'll do that in a minute. But before we do, what sort of things do you think that we need for a practical stability session, whether it be in a classroom or on a vessel? Again, just call out.
Water.
Water. Okay, so what can we do on a boat to get water? Where can we put water on a boat in order
In the sink?
In the sink. Okay. What else do we need, or what can we use while we're afloat? You know, if we don't have anything, what can we actually use? What can we make?
I do pretty much everything with a bottle of water.
Yeah, you know,
almost all the demos with it.
Chop it in half. Okay.
No,
add some. Don't forget, you'll need a keel. You need something to keep it upright. Okay. And what can you use as the weight?
Blue tack.
Blue tack. Okay. I've seen people use pennies before. Okay. However, I've got the deluxe version. So basically, there's my tank. Okay. Here is my model. Okay, my police boat. And this is good because you can take off the actual flybridge, which is brilliant.
Lucky Julie's left. She'd be jealous right now.
Ah, and I've got my jewellery weights. Okay, so 200 grams, 100, 100, 50, 25, 25, 25. So these can be bought for about £6 off eBay. Okay, if you search on eBay, you'll get them, no problem at all. And I have 2 boxes in order to make sure I've got enough of the weight. So what I'm going to do now is I'm going to hopefully not trip over the tank and place the laptop in the tank. I'm going to place the laptop on a platform so that we've actually got. So if I take out of, stop the sharing on that for a minute, so you've got my full picture. La, 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 la. Let's angle it down towards the tank. There we go. Right, can you all see the tank?
Yep.
Yep.
Fantastic. So the first thing I'm going to do...
But we're still all here. I thought you wanted to go to full picture, Gary.
Yeah, you want to... What, me to go to full picture or you guys to go to full picture? Because if you go to full picture and I'm talking, you should just get me.
Yeah, you need to click on view, speaker view.
Let's have a look.
So on the top right of your screen, David, you'll see if you hover, a little view icon appear. If you click on that, you should have speaker view and gallery view. If you select speaker view, whoever's talking will appear large on your screen.
Yeah. Is everybody happy then? You can all see it? Brilliant. So the first thing I'm going to do, and I'll try and maneuver it so I can show you, is the actual incline test. Okay, so what I'm going to do is I'm going to add weight, okay, to the side of the vessel. So basically I've got my chair there. Can you all see that? So you add the weight to it. As you can see, it's heeling over quite nicely. Let's add another bit of weight. So that is 300 grams. Just move that forward there. Okay, there's the weight. There's the boat heeling over. I would say I'm going to add another 50 grams to that. And as you can see, we've got down flooding, okay, before AVS. So that's your sort of very, very short incline test. What I'm now going to do is I'm going to add the 200 meter grams, okay, and these are the engines, okay. So I'm adding the engines to the vessel. Let's just get rid of the water from there. So an engine there and an engine there, okay. And what I'm going to do is I'm going to do the incline test once again. So again, I'll add my weight, and again, see exactly what happens. I've got the results a bit later on, but as you can see, a lot less weight will tip the vessel, okay? And that's largely due to the decreased freeboard of the vessel, but also the fact that you've got weight. Even though weight lower down makes the whole thing stiffer and makes it less tippy, it's still a case of you've got more weight on the vessel. What you've got to do is you've got to have higher sides in order to make sure that that weight doesn't get to the down flooding angle quite quickly. The next thing I'm going to do is we sussed out that nigh on about 350 grams was enough to tip it. I've got the fly bridge on now. So what I'm going to do is I'm actually going to add weight to the fly bridge. I'm going to start low this time. I'm going to start with 100 grams. So as you can see, just 100 grams of weight is producing that heeling. Okay, actually it's listing because it's weight. Let's just do a 51 on there. And as you can see, we are very, very close to our down flooding angle. Okay, so all I'm saying is think about the model, think about how you're going to put weight on it and how you're going to demonstrate this. Next, I am going to add a bit of free surface effect. Okay, and again, you can go back and do the incline test. Let's take off the fly bridge. Let's do the incline test again. And you'll probably find that with a little bit more weight of water on that side, okay, with the free surface effect, it's less weight to take it over. So some very, very quick, okay, that's why I'm wearing short sleeves today, so I don't get myself a little bit. Let's take us back to there. I had some things. I think what I've got to do now is I've got to basically use an extra camera or do something to that end. So let's share the screen again. There we go. So in our first test then, so we did the normal incline test. We added weight to one side, okay, and what weight will the boat down flood? Well, I put it basically down to about 350 grams. You could measure it in pennies, you can measure it in nuts and bolts, whatever you like, so long as you have a value there. What angle will the boat experience down flooding? I recommend for my little plastic boat about 30 degrees, but obviously it'll be a little bit more for actual vessels. And basically what your observations and conclusions were. For the next test, we added a couple of engines. Okay, so what happens to the boat when the weight is added? Well, it becomes stiffer. Okay, there's more weight, and hopefully you're actually introducing more weight lower down, so you're lowering the center of gravity. But what you're also doing is you're also lowering the freeboard at the same time. So that's something else to consider. What you've taken away with what you've added in one, you've taken away with the other. So lower freeboard, much less prone to heel over, okay? But the lower freeboard is there. Do the incline test once again, and we added the weight, and it was much less weight this time round. Did the downflooding occur earlier or later? It occurred earlier. What effects does this have on stability of the vessel? Better stability due to the lower center of gravity. However, it had a lower freeboard. Finally, we introduced weight aloft. Okay, so 150 grams was enough just to take it over to the brink. A slight little bit more would have actually instigated the downflooding. So obviously, the higher the weight, the less weight it is to take you over to that downflooding angle. Okay, so much less weight. So that's 200 grams less than the actual first incline test. What happens before the capsize? Downflooding, of course. What angle did it start to occur? 30 degrees. And then we basically added water inside the hull. And of course, the answer was fairly simple. So let's unshare my screen. Excellent. So let's have a chat. Let's add to mine. Let's just share the screen again for the questions, actually, to be honest. Just getting to grips with this thing. So, any conclusions from the last 4 practical demonstrations? Anybody?
I probably need to add a little bit more when I'm teaching courses to my stability chat.
Okay, what sort of stuff are you thinking about adding?
I think a little quick practical demonstration with a bottle or something along those lines, just to reinforce the issues of down flooding, which is something I mentioned but don't really go deeply into. And I think it's just looking at what you've done, that would be an area that I could really give some value. Fantastic.
Okay. Anybody else got anything about conclusions from the last practical demonstrations?
Yeah, I thought they were really useful, and I'm going to pinch exactly what you've just done. I'm going to go and look for some eBay model boats straight after this. I teach the same theory as you, as in I've got similar graphs and so on, but actually some people they switch off a little bit with graphs, and your bottle demonstration is blindingly obvious and really demonstrates a point. And then the test tank, as you know, my classroom's got a sink in it. It wouldn't be difficult to replicate that. So I'm gonna thank you and nick that little last 10 minutes. I think that's really, really useful for me.
When they're playing around with water and boats, they love it, and again, it reinforces things. I think what you've got to do is steer them to what they're looking for initially, and then they'll find it. Yeah, it took a while to find the right size boat and the right size weights, you know. And I should imagine what's going to happen now is I'm going to go onto eBay to Playmobil boats, and there's going to be some pretty high bidding going on.
Okay. No, I'm going to go to kids' playroom and find one.
Yeah, you've got that luxury, Doug.
Yeah.
So how can we teach stability to students when we afloat train? I think we pretty much more or less got the nuts and bolts of this already.
I mean, when it's a float fair, I don't see me ever taking model boats on board a boat to teach it. You know, there's enough kit we've got to travel about with as it is. If there's one on board, then great. And in the classroom, I can see me using that technique. So I suppose the model boats, although we do have a sink, it is restrictive on board. Yeah. I mean, I always use a bottle of water, and if you fill it up to about there, you can demonstrate the weight and the stability of it, the free surface effect, the balance points. And so I find just one bottle, you can teach it all with that. But I do find the having the model boat from the classroom is fantastic.
Yeah, yeah. Okay. I think we've already entertained what items on board our boat to demonstrate stability. That's no problem. We've done that with the classroom as well. So here's a good question for you. Now that you know about this subject a little bit more, what sort of time are you actually going to dedicate to actually teaching stability to your students? And on what courses are you going to teach your stability to your students?
Well, I think it doesn't need a massive amount of time, because you can actually do it. If you do it practically, you can show people on a rib by moving about and all that sort of stuff. And on a motor cruising course, you can use a model and you can spend a little bit of time and put it in practically without spending a lot of time on the theory. So, but it's that practical element that will nail it for most people, I think.
Yeah, I would probably say the same. You know, you're either stop for lunch and quick 5 minutes sort of thing. What sort of learning points do we need to get over to our students? Okay, so what sort of things do you think that you've taken away from this that you need to apply to your students? Obviously at a lesser level, because obviously what I've done is I've brought this up a bit in order because I'm teaching instructors. But what sort of learning points do you think you should reinforce to your students on that level?
One of the things that really came home to me, Gary, when one looks at the Yachtmaster notes or any other DIY books, It will show a stability curve, mainly for sailing boats. And then it shows the curve for a motorboat with a line that says, you know, this is the point of down flooding. And the two aren't kind of related. And the fact that that curve goes on and you get to your angle of vanishing stability, it's never there because it's always sailing orientated.
I mean, when you're talking about down flooding and then you're going forward towards AVS, you're not bothered about AVS. It's coming anyway. You know, the rest of that curve is quite frankly quite irrelevant.
Well, that was the learning point I've taken from this, because I, frankly, show my ignorance here, it hadn't dawned on me. So that was brilliant. Thank you.
No, you're more than welcome. Okay. Anybody else got any learning points to put forward to students on courses?
Yeah, but I mean, for PB2, I think free surface effect, that's the thing they're going to come across mostly. I'm actually doing some practical with a tank of water somewhere and a model boat, actually, to show free surface effect. I think I might try and work that into the course a bit more.
Lovely. Okay. Anybody else at all?
Weight aloft as well, how that affects it. You know, certainly on the sail side, you're seeing it more and more with the solar arches and dinghy davits and more stuff being piled high up.
I think one thing I had a bit of a look at, I remember when I was actually chief instructor on deck, what Stu did at Commodore was he put an extra deck on his canal barge as the main sort of classroom cum accommodation, and that just didn't look right. And it was a case of that again, you know, I think you need to get a stability test done on that. And yeah, they did have to add, you know, a bit of ballast to that as well, actually, which is quite fun. But yeah, weight aloft, you saw how it was, you know, 200 grams less, and there's not really much height in it. So when you're talking about the amount of people on the flybridge on those two small 34-foot boats, that was enough to take them over. So, you know, quite stirring. Okay, fantastic. Right. Well, I think we've basically chewed that.
I have a question as opposed to adding. Rather than searching around on eBay, do you know where you got that little police boat and the weights?
The weights were from eBay, but jewelry, there's a lot of jewelry shops that will give it to you. I mean, one of the handiest things that I've ever had, it's completely unrelated, is a jeweler's monocle, which is actually 35 times. So when you're looking at small print on you know, serial numbers on things and small print, that's actually perfect. And I got the weights from eBay and from there as well. The Playmobil police boat, you're talking, well, it's just toy shops really.
It's a Playmobil.
It's Playmobil. Yeah,
fine, thank you.
You know, there's the captain, David.
Fantastic.
That's me. Except I don't have the white hat on because it puts age on me.
Gary,
okay.
What was the range of weights you're using?
The large ones for the engines were 200 grams, and then you're talking 150, and then went down to 25.
Okay, thank you. I'm on eBay now.
That seemed to work. Okay, so in summary, what we did was we looked at the center of gravity, the center of buoyancy, and how the two interacted to form the righting moment lever, which was GZ. We looked at how the righting moment lever was documented in the stability curve. That brought us home to the fact that we've got angle of vanishing stability and then the negative GZ in order to fully invert the boat. We looked at different boats and different characteristics. So next time you go down to the jetty, you'll have a look at different features on motorboats. Flybridge, okay, that's ringing my alarm bells, so on and so forth. We also did motor vessels, what helps and hinders stability, and you found that compared to yachts, we are on the back foot because obviously smaller keels, you know, higher superstructures, just a couple of the things that will affect stability. We looked at how moving weight, both vertically and horizontally, affected the righting moment lever, and we confirmed that with some case studies. We also had a look at down flooding and free surface effect and how it can dramatically add weight to your vessel and how that weight is moving, dramatically moving the center of gravity, and how to sensibly load your vessel. Always adhere to the paperwork, and there should be a CE plate on your vessel giving you the minimum loading, or the maximum loading, I should say. And for the group chats, we've had some brilliant ideas. Thank you very, very much. So, anybody got any final questions before we wrap this up?
No, Gary, just on, because Nikki and Steve aren't here, so on their behalf, they've asked me to thank you for your time, mate. But from me as well, that was brilliant. Thank you so much.
No, you're more than welcome. You're more than welcome.
You've done a great job there. If there is any opportunity for you to upload your PowerPoint stuff that you did towards us, there's some great little crib notes on there that would be useful, I think, for the whole group and anybody just to refer back to. So if you don't mind sharing that,
yeah,
that'd be
absolutely
brilliant. Thank you.
I'll see what I can do, but you know what I'm like with my presentations. Anybody's welcome to them.
I know, mate. Same here. I've got. I think I've got all of yours.
Yeah, these are in Mac, okay, because I do like Keynote better than PowerPoint. But let me know if you're a Microsoft Philistine, and I'll transfer it over to PowerPoint for you. Okay, so that basically is that's all, folks. Okay, and there's the fireworks. Thank you very, very much indeed for your attention.
No, thank you.
Okay. I am a Philistine, so PowerPoint, if possible, please.
No problem at all.
Yes,
just let me know on your. Just let me know. You've got my email address. Just let me know on the email, and I'll happily see what I can do. I think Dropbox might be the way to go because there are rather big files.
Excellent. Thank you very much.
Really, all right.
Okay.
Thank you very much.
Have a superb rest of the day, guys. I've got another session at 2, and I'll see you later.
Thank you, Gary. Goodbye.
Thanks,
Goodbye.
Gary. That was really
Can you leave it open a second while I grab these links, Gaz?
Yeah, no problem at all. All I'm going to do is stop the recording.